All right, and now we have Aditi from UC Berkeley who will talk to us.
Great, thanks. So this talk is definitely going to be very overlapping with some of the themes we've seen in other talks. I'm actually lucky to go after Rafa because there's actually some introduction I can cut out now. So more fun things that we can talk about going beyond that. Cool. So I'm gonna just start by putting this up here. So on the x-axis, number of years of math needed to understand the answers. The y-axis happens to have philosophy that we see around a lot, actually, particularly in Berkeley, if you're ever walking around campus. But the things that I'm going to mostly talk about today are actually going to be related to quantum mechanics, but I'll also talk a little bit about fluid dynamics and how those things are actually the methods that we use on the machine learning side can be quite synergistic with each other in terms of the different types of problems that we typically look at. And I also just want to put this up here to, I think, a common theme that we've really noticed in all of these talks is that we're really trying to solve some very difficult problems that have taken centuries to solve through other methods. And so what are the solutions going forward, but also using all of that knowledge that we had from numerical solvers, maybe some of that information can also be relevant when we think about these problems in the machine learning era. So this is, I think to this audience, this is very common information that one of the key points of understanding scientific phenomena is understanding the spatial and temporal behavior over time, whether it's things like adsorption, catalysis, gas storage, any type of fluid mechanics, weather patterns, protein dynamics. This is all really tying down to how can we model spatial and temporal behavior over space and time, and how can we accurately reproduce that type of information. And there's so many examples of how interesting things happen at really long timescales. So this is, for example, batteries rely on very long timescales to see behavior like the charging cycles, to see things like degradation. There's also it's like a fluid dynamic simulation of an airfoil. And this is very critical because if we didn't have these types of simulations, we probably don't want to fly airplanes. And there's also, of course, things like protein folding, another grand challenge. How do we actually simulate these systems over time? This is a really hard one because we want really big systems that we want to see over orders of magnitude timescales. So I think given that and how important these problems are, there's of course been a range of approaches for tackling these problems, starting from something that you might do on the experimental side with validation. There's also this whole set of numerical methods. We have finite element methods, we have density functional theory, we have molecular dynamic simulations that have all been developed over time just to tackle these really hard problems. And of course, in the last few decades, machine learning has come out as one possible approach that could augment or help with these big problems. And I think one of the challenges also here is how do we, at a very high level, generalize to new problems using these methods? Because if I have a finite element solver, I can go use it for one PDE, and then I can go use it for another PDE, and I have pretty good bounds on the accuracy and the convergence. Of course, other issues on the efficiency side, but those same guarantees are not necessarily there with machine learning. And the theme of this talk is really going to be about how can we use implicit information that we might get from things like numerical methods during inference and during simulation time. So I wouldn't say it's cheating, but we are actually keeping in mind that there are distribution shifts going on when we actually deploy these methods. And so how can we account for that during our training process itself? So the overarching themes of this talk going along those lines are really going to be about this idea of how do we do or how do we use implicit information? How do we improve this simulation reliability to new problem settings? And how can we actually look at the intersections between simulation, numerical methods, and machine learning? So the first half of what I'll talk about, it's good that I'm going right after Rafa, who's actually warm-started a lot of the introduction and background to molecular simulations. So improving the stability of these molecular simulations, how do we actually get to do reliable simulations and observe and reproduce the types of observables we want to see over time? And the thing I'll talk about here is a type of simulation in the loop type training strategy. And one of the nice things about such an approach is that you can potentially also incorporate experimental information into your training procedure. So this is combining some level of simulation data with other observables, which could come from things like experiments. And the second thing I'll talk about is this idea of conservation laws. So the world is physical, and there are certain laws that we do know hold true. Now, I know it's been a topic of discussion at this workshop of to what extent should you actually incorporate those conservation laws into your machine learning model, particularly at training time, because that can make optimization more difficult. And there is this trade-off of what we might see in the physical world is different from what we might see when we do neural network optimization. And so the theme of this part, even though I will talk about conservation laws, one thing I'm emphasizing here a little bit more is these constraints at test time. So at training time, maybe that's the case, but at test time, there are certain physical guarantees that could be nice to have, could be nice to actually help us give reliable or meaningful answers. And on that note, I'll talk about PDE constraint optimization, how it can be incorporated as a layer in neural networks, as well as the intersections between things like spectral methods have been used in scientific computing and applied mathematics. How does that intersect with neural networks? So very general overview of molecular simulation. I think I can go reasonably fast through this since there's, again, been a lot of talks touching on some of these common themes. But if you have some type of molecular system, typically this is something on a potential energy surface, and you would like some function to estimate that potential energy surface. You could get energies and you could get forces from that. And then you can go ahead and do some type of numerical integration with your favorite symplectic integrator, integrating Newton's equations of motion to get the next time steps. And the key point here is that this is all a stochastic process, so we are thinking a lot about distributions when we do this full cycle. So this is, I think, again, to this audience, I think many of you are convinced that there are very many interesting ML problems in molecular simulations. But just to put out there, I think why this is such an interesting area on the ML side, of course, it's hugely impactful on the scientific side, is because there are these open problems of how do you simulate these systems over long time scales, because that's often what you really need to compute properties that you might care about. So you might want to run this for a really long time, and then you can compute some type of observable about the system that you're interested in, and often that takes many, many time steps. And the other challenge is also, if we want to study these systems well, it has to often be at realistic atomistic sizes. So we often want to study systems that are really large, many, many atoms. And that does mean that we have to compute forces and do numerical integration on each atom. So that's another potential bottleneck there. And then I think there's some interesting topics here along the lines of physical consistency. So this is a stochastic process. There's thermodynamics that we have to keep in mind. And this is another area where it can also go the other way, as we saw in the last couple of days, this idea of using this physics inspiration in ML as well. So coming back to this overview of how we would typically run molecular simulations and this full molecular dynamics cycle. So when people typically try to do machine learning for these problems, the most common way is to use some neural network to estimate the potential energy surface. So this could be like your proxy, your oracle, that will hopefully give you an answer much faster than whatever numerical method that you are using here. And you can potentially also think about doing some type of machine learning on the actual integration process. This is a bit less common for a number of different reasons. So I'll very briefly go over some of the components here. This talk is going to mainly focus on the last point, the training procedures. I think some of the other points have also been very nicely touched upon. So if we're looking at these data sets, typically you have some type of 3D structure. So I equals 1 to n, and hopefully n is getting larger and larger. And you have some DFT labels, so quantum mechanical simulation labels that go with this. So energies, forces, other properties. One thing is that with DFT, those labels in a way come for free. So there isn't quite the same notion of non-supervised learning settings because of the fact that we do get this with every atomic structure. And there's also DFT is fairly nuanced, so it means that there are going to be many levels of accuracy depending on how you do your DFT computation, and that could have some effect on the output of your predictions or the quality of your predictions. So the most common way, or one of the most common ways that people are now doing machine learning with these molecular simulations is using standard, like some type of neural network to estimate that potential energy surface. And there are many design choices for how you would do that, many discussions about to what extent you might need certain symmetries encoded. What is that trade-off with efficiency? Because typically you want something super fast. If you're going to run this for 1,000,000 time steps, you need something that's actually going to be tractable to do that. I think that's an open question right now in how to make these less heavy duty. Some of the things I'll talk about today around training strategies, both in the molecular context and in the fluids context, are fairly architecture agnostic. So there are going to be methods that you can add on top of your favorite architecture or whatever the state of the art is for a given architecture. So finally, coming back to this idea of training procedures. So like I mentioned, supervised learning is the most common way that you would use to estimate this potential energy surface. So you could have your favorite quantum mechanical data set, you train it with your favorite neural network potential, you take a loss function on energies and forces, and of course you train with backprop. And this is essentially the goal is that hopefully you have a really good proxy of the potential energy surface, so you can then go use it in downstream MD simulations.
Quick question. Again, on the force fields. So the input should be of this kind of learned force field is probably a number of atoms that are variable in size or in number. Do you use some sort of deep set architecture to assure this?
Yeah, so you mean like the neural network architecture itself? Yeah, it's most common these days. The most common way people do this is typically through some type of graph-based method. So you could use a graph neural networks to have some notion of what the atomic positions are, but then you're now training them to the energies and forces that are the labels that are tacked onto those atomic positions. And I think with this picture, I think when you look at this first part, that this is the main technique, that you have this data set, you do supervised learning. I think there's a lot of challenges that do come up in terms of getting this complete picture, because it's very easy to not have a complete picture of your potential energy surface. And for a number of reasons, so you might need a huge amount of data to actually get a true understanding of this potential energy surface. That's going to be expensive. These atomistic systems can also be really different. So there's huge chemical diversity in whether you have a catalyst system versus a bulk material versus a molecule versus a protein. And so it's really hard to try to think about how do you span all of these different types. And even the energy and forces labels that you get, they can span many orders of magnitude. And this is something you could correct for with things like normalization, but I think it becomes hard when you actually go and use these downstream to capture that type of behavior. So if we put together the full procedure here, typically the way this works is you go ahead and train your neural network. You have the atomic structure and you're matching it to the energies and forces. You might go ahead and compare that energy and forces error on some test set. So this could be just a held out test set. And hopefully if that error is sufficiently low, you run molecular dynamics simulations with the trained neural network. So you just run this cycle many, many times until you get the next time step. Of course, we also heard about other strategies like active learning that you could potentially also do if the energy is not, or the energies and forces are not sufficiently low to try to still drive them down when you actually run the simulation. So the thing about this approach is that training objective and the dynamics behavior that you see are not always in exact sync. So after you go through all of those steps, and we'll go ahead and run the MD simulation, sometimes you can run into some potential issues with actually running it over time, where this is not what we would hope to see, where you have these really large bond stretches. Here's another example here where everything looks great, we're running it over time, but as we keep going further and further, you get something that would not be the type of thing that we would want our neural network to predict. So these can also show up in other ways. Sometimes I showed the bond stretching here, but you can have two atoms fall on top of each other or get very close to each other, which also will completely mess up your simulation because your energies are going to get very high. So this is so this idea of stability, again, Rafa touched on this as well, where when you actually run the simulations, you can run into some of these instability issues that actually pop up regardless of the time steps that you're using sometimes. So this is actually another discussion, but this can happen even at very low time steps. And of course, this poses a lot of issues because you can't run these simulations for long time scales, which means you can't capture the behavior and the properties that you care about that you would get from those long timescale simulations.
If you had an inaccurate or low quality DFT calculation, would you also get something like this if you didn't get over long time steps?
Yeah, I think it actually could potentially be worse if you have a really bad DFT calculation. I think you're probably much more likely to run into this type of behavior sooner.
So how do you know if this is arising from the DFTs you trained on versus pathologies of the neural network?
I think it's probably a mix of both. You hope that if your DFT calculations are good enough, you'll have some type of at least reasonably smooth potential energy landscape that you can run through. But it also probably arises from the fact that the neural network doesn't have a complete picture, especially as you're running these simulations over time and ending up in new regimes. So these failure modes show up in a lot of different ways. And again, you have these global instabilities where things may stretch really far out of what is considered physical. And you could also have different types of local instabilities where maybe two atoms fall on top of each other and that blows up the simulation in other ways. And it actually, these failure modes actually can vary for different systems, different ways to look at these problems. And so it's actually important to think about how can we have some overarching way to address all of these failure modes at once, given that they actually show up in very diverse ways. So another way to think about this is actually with a perspective on the potential energy surface. So this is just a schematic. This is not precisely what actually happens, but I think we hypothesize that it's for reasons like maybe in one case, you may have learned a potential energy surface, but when you run that simulation, you're landing in a regime that you've never seen, and so the simulation just blows up. Or maybe you're supposed to be going down towards some local minima, but you go in another direction, and again, that shows up in how the simulations are actually run. So I think I would actually call this a really classic case of a distribution shift problem, where you really are just moving out of regimes that you haven't seen, and so you don't have that complete picture. So how do we actually go and prevent these failure modes? And we come back to this training procedure here, where we've trained this neural network on quantum mechanical data the whole time. So we've trained it on theory and simulation data. And a natural way you could prevent these failure modes, well, you could get more QM data. So active learning would be one way to do this. Some challenges there are that you might need a lot of data, and it might still not be enough. If you want to go to the really long time scales that we care about, you may inevitably always keep running into these failure modes.
Like classical force fields, like not even quantum mechanical ones, don't have these instabilities, right? They don't capture a lot of important physics, but would it not be enough to pre-train a model on tons of just classical simulations to get the basic physics of like bond stretches correct, and then train it on a smaller amount of QM?
Yeah, so I think actually I won't explicitly talk about that today, but I do think that that is also one way you could start to get around some of these issues. So there are two issues here, though. Like one, I focused a lot on the stability issue. The other thing is also when you run the simulations, are they actually reproducing what you want them to reproduce? And that issue also tends to crop up. But I do think this idea of using both of these data sets actually could have a lot of promise. The issue is sometimes for some classical force fields, for some systems, at this stage, they're very bad right now. And so that also makes it complicated if they're completely uncorrelated to what you would get from QM. So in this talk in particular, I'll talk about training strategies in general. And the main thing I'll talk about here is why not actually use the simulation to capture more data about the systems that we care about? So going from purely DFT energies and forces, are there other modalities of data that we can exploit here? So if we go back to this molecular simulation, we're running the network. We have a neural network to estimate the potential energy. We're integrating this over time. Well, if we run this over time, we can actually compute properties of interest that we care about. And that's the ultimate goal of MD simulation, not necessarily to get really low errors on energies and forces, but actually to reproduce system observables that we care about. And so if we take this, everything in the red box here, and we go ahead and run this MD simulation, so we run it, unroll it for many time steps, you can assume we're going to a million time steps, maybe more. And let's say that we run that simulation. At each time step, we query the neural network, run this out, and then we can go ahead and compute system observables about these systems from that trajectory. Now, of course, if the simulation is not a good one, these observables are probably inaccurate, but nevertheless, we can, in theory, compute these observables. So what about also actually then training to those observables? And this is more colloquially would be considered maybe like a top-down setting, but I think the key idea here is that we're not throwing away all of the DFT data as well. We're still using that theory and simulation data. And I think the bonus here about doing it in this style is that you do get multimodal sources of information. So you might get simulation data to train your potential, but everything else, the system observable, you could in theory get from an experiment, and you could try to bridge some of the gaps between these two areas. So coming back to this process, so this Boltzmann distribution is something we've already seen a number of times. So molecular dynamics, as you run it out and you converge to some equilibrium distribution, is essentially like drawing samples from a Boltzmann distribution. So your probability of being in a given state, dependent on your position and your momenta, is going to be a function of this Boltzmann distribution that is going to tell you something about how the system is behaving. So this is how we formulate our learning problem. So if we want to train to these system observables, it's a stochastic problem. And so we can frame it as we want to maximize the expected reward of reaching that observable under some type of Boltzmann distribution. So this is essentially the reward that we hit that observable and we computed it correctly, along with the fact that we know that we're sampling from this Boltzmann distribution. And so putting that up here, so this is our learning objective that we're trying to work towards. Sure. Yeah. So basically, our goal is that we want to, in addition to doing DFT training, we're running the simulation in the loop, and we want to train it to whatever we know that we are going to converge to some system observable that we should care about that reproduces something about the system. So we want to train to maximizing the fact that we are getting the value of whatever observable that is correct. But we know that this is also under a Boltzmann distribution. That's the probability distribution that we're sampling from.
You want to minimize the variance of that observable, basically?
Yeah.
So I guess you want like a low variance estimate.
Exactly. Yeah. Exactly. Yeah, so this is basically how we're treating the learning objective after we've already trained a neural network potential on some type of DFT data.
What is the advantage of formulating it this way over the way that people typically do this, like max-cal, where you basically are just using a Lagrange multiplier?
So I think the issue with that is that you're not directly tackling the fact that you're seeing these instabilities. So I'll actually talk about how you can use this in conjunction with actually finding instabilities in your simulation. So the
function is defined how?
The reward function could be whatever observable you know should be true about the system. So it could be as simple as like a radial distribution function, but it could be a more complicated thing about the system.
Maximize like minus a discrepancy between that.
Yeah, exactly. So I'll get to the point about how you can use this within a full training cycle. But the key point is that if you're going to train a neural network to these observables, you do need to be able to differentiate that expected value of reaching that reward with respect to your parameters, just to be able to train this full thing in a loop end to end. So you could try to do direct differentiation through that molecular dynamics trajectory. The issue with that, though, is that if you've taken a lot of MD steps, you've called this numerical integrator a bunch of times, you are storing the gradients along the way. And so when you try to do some type of direct differentiation through this, this is going to be both computationally expensive, but you'll probably also run out of memory pretty quickly as you try to do that backpropagation step. One thing, though, that you can use here, and this is going to be one of the general themes of this talk of combining numerical methods with neural networks, is that in this case, the individual sampling steps don't actually matter because you're sampling from a distribution that you get to and that you converge to over time. And so because these gradient steps are independent of the sampling, you can actually formulate this as an implicit differentiation problem. So before, you might have had some y is equal to f of x, as this is your standard output of the neural network. You can reformulate this as, say, you have some function g, and g of x comma y is going to be equal to 0. And that's something that you can actually deal with instead and differentiate instead. And what that effectively is actually doing is it's decoupling the output that you get from the neural network and the solver. So whatever, all of those unrolling steps that you took, you're completely decoupling that from the backpropagation step that, that you use to actually train the model. So you're not going through the forward pass and the backward pass in the same way. And because they're totally decoupled, that means that you can actually train the neural network in this way by accounting for the fact that you can use this insight about how you formulate your learning objective. And so the full simulation then is that you go ahead and run this MD simulation, you compute something and take a loss function, and you use this idea of implicit function theorem to train the full model and use all of the information that you might have. So this is the learning objective that we're trying to solve, and you can see the full derivation in the paper, but this is essentially what we call a Boltzmann estimator that allows us to train the neural network and get gradients to train it both with DFT data and the simulation data. And what's interesting is actually this formulation here. There's you can actually get this. So we did this through implicit function theorem. You can get this actually through reweighting or through policy gradients. So there's many paths to getting to this point. But one thing here is that this is a more general framework, so you can actually frame it and derive something for local instabilities as well. So in many cases, like condensed phase systems, you often have local instabilities, and this type of training procedure can also extend to those settings too. Oh yeah, so G of gamma is the notation that we use for the observables, and gamma is how we're grouping the position and the momenta of this atomistic system. Those are the things that we're trying to evolve over time. So that's the probability distribution. So the thing is that we, actually I'll talk about this maybe in the full training setup, why it's useful to maximize this observable, because it actually helps in terms of guiding the neural network to avoiding instabilities.
So now, like a larger observable is better?
Not a larger observable, yeah.
The reward should be expectation of the mean squared error between G of gamma and the reference. That's the reward.
Yeah. Which it'll make more sense when I show the full picture altogether, because that will be in the full picture. Yeah.
Does that mean that's a typo or?
Yeah, it's not.
Okay.
Oh yeah, sorry. yeah.
It's not G of gamma. It should be.
It should be
the mean squared error between G of gamma.
She's like a target value.
Yeah. Yeah.
You want to minimize that.
Yeah, exactly. Yeah, that's the thing that you're minimizing, but it's the opposite of you want to maximize that you will reach that state. Anyway, so putting this all together, this hopefully will be a little bit more clear about how you can do these two things in conjunction. So you can start off with this typical quantum mechanical pre-training step. So this is the usual way people would do this. You train to energies and forces. So this is the correction step that puts together this whole idea of why we care about training to observables. So you can take your favorite pre-trained neural network, your favorite architecture, and you can put it through this cycle that we essentially call stable training, because it's something that is actually keeping track of the stability of how good that potential is. And we're using this idea of a Boltzmann estimator to train it to the relevant observable. Yeah.
Does stability mean how close are you to the target observable?
So in this case, we're defining stability so in this case, like a bunch of simulations are run in parallel. You see where they start to break down, and at the point where they all break down, you can then come back, reset, and then train with this observable training. Yeah, so there's a few, so it depends on the metric that you're using to catch those instabilities, but one case could be two atoms get too close to each other, the energy gets really high, and so that simulation is probably not going to be relevant anymore. The predicted energy could get high, but also it could be something that propagates when you run this simulation over time, that the error gets worse and worse because of initial little things that are breaking the simulation.
But somewhere you have like there is a lookup, like a prior of failure modes.
Yeah.
Says that the simulation sort of broke those priors that
Yeah.
we're not capturing the model, but you know that they apply, right? So contact,
Yeah.
ball breaking.
Yeah, exactly. So there are definitely priors that we keep in mind about the system ahead of time. So that's actually why, say, a liquid system will break in a different way than a molecular system, which could break in a different way than a protein.
But you have a predefined set of rules that you look up as well.
Yeah, but most of those actually end up being general heuristics that apply pretty broadly to the different failure modes or the different systems that you're looking at.
In some sense, the traditional way of just like predicting DFT output, like you can think of that as like the identity observable, like, and then here we're just adding like other functions of those other. So now we're doing basically multitasking training.
Yeah, I mean, so sort of, but I would say that I would think of that more as that you start with your pre-trained step, you add the observable to your loss function, and maybe that's one way you could do it. In this step, we're actually doing this explicitly in this simulation in the loop style. So we're simulating the system and then computing something and then training to that. So it's almost like you could think of step 2 here almost like a fine-tuning step, that this is now a step to figure out where all the instabilities were from your pre-trained model and how to correct them. And so this basically means that you're initially training, you're running the simulations and training to observables. And the key point here that's different from things like active learning. So active learning is not mutually exclusive to this setup. You could, in your step 1, do a bunch of cycles of active learning too. But the key point with this second step is that you don't need to do extra DFT. So you don't have to do that particular cycle and do extra computations.
Super nice. Although if you have this lookup table of constraints, like why don't you just bake those into the learning of the potential in the first place?
Yeah, so the constraints, so there's certain things you could potentially try, like if you have bond stretching, maybe you add some type of kx squared term to constrain it to not go beyond a certain point. It's a little tricky to do that though, because adding a constraint somewhere can mess up something else somewhere else. So it's a little hard to account for potentially all of those situations.
You're saying it's better to identify that you've hit one and then not treat it as a constraint, but do something else.
Yeah. Yeah, exactly. So this cycle essentially, yeah. Cool. So I'll just talk a little bit about some of the results that you get from this type of fine training procedure. So in this case, suppose you have some molecule and you have some reference quantum mechanical data. And on the x-axis, we have the simulation time of how stable this is running. So ideally, you want that time to be large. And on the y-axis, we have the number of simulations that are run in parallel over time. And so if you have 1K QM data, so that's the blue lines here, and when you go to like 50K QM data, you do go a little bit further in stable simulation time. So it's a little bit hard to see here, but the gray curve is going further out on the x-axis than the blue curve. But if you actually do this type of, just with 1K training data, you add this training procedure on top of that, you end up all the way on the right-hand side. And we did the cutoff at the axis on the right-hand side because at that point, I think the point had been made. This is just one example of you can potentially get some savings on the QM data that you're doing by actually doing this fine-tuning procedure, which is going to be looking at and getting different sources of information. Another example here is our favorite water system. So in this case, this is actually a case where you might have these local instabilities. And on the x-axis, you have the simulation time. And so ideally, you want that time to stretch further and further out. And we only did this with 1K training, so you could definitely train a really powerful potential that will push the boundaries further. And then you could still do this type of training on top of that when you run into those instabilities as you're running this for thousands and thousands of time steps.
So the way you're measuring instability here is the same definition you put into the training.
So the way we're measuring it here is, yeah, it's not always the same definition that we use in training. Sometimes the one that's used in training is actually different from the one that we measure. But this is a different one and different definition that we use compared to, say, the molecular system I just showed.
Sorry, is the improved stability coming from hitting the thermodynamic observable better, or is it from some other part in the training procedure that's adding? Like, I wasn't sure if you were saying that you also had some stability loss.
Oh,
I also missed that.
yeah. So I think probably a chunk of it is coming from training to the observable, but the training cycle of running these until they don't converge, then rewinding, and then training to the observable also probably plays some role. But I think a lot of it does come from the fact that you train to the observable as well.
I didn't understand what's actually happening. So you run it, it gets unstable.
Yeah.
You rewind it. If you how are you then fixing it so that it doesn't?
Yeah, I see. Yeah. Actually, I think I may see where this is coming up. So finding the unstable region is like some heuristic that we use. We're not training to that heuristic per se. So we're using that heuristic to find this is where all of the simulations become unstable. Then we actually go and do this training procedure with some observable about the system. So the heuristic about stability is only used to find where all the failure modes are.
If you're hitting an unstable region in the simulation, haven't you not integrated enough to compute the thermodynamic observable?
So that's why at that point when we hit that unstable regime, that's where we do the rewinding to go back X amount of steps and then train the model at that point to the observables. And ideally now it's going to be less likely to hit that unstable regime.
I'm confused. I thought you're training it to hit I thought there was a multi-objective that was with the forces and the energies and the observable.
No.
You're
So
turning the observable on and off only if it's in an unstable region.
So the energy and forces training is completely separate. So that's our step one. That's what we do initially. After we do that, we do this observables
So
training.
pre-training.
That's just pre-training.
You could end up forgetting that entirely based on
So-
reading the observable.
It's possible you could forget that entirely. It's not. So one thing we do that I don't explicitly say here is that we do regularize with the same energy and forces data that we used in pre-training. So that's still done till convergence, but we do add that regularization term just to make sure we don't fall too far away from energies and forces. But it's not any type of new data in that step.
One question, sorry. This may be not from the gradient estimator in time, but any thoughts on this? How does it relate to like kind of classical Boltzmann learning of observables, like Boltzmann learning fine tuning with like a replay buffer? It looks like it kind of seems a little familiar.
Yeah, I think maybe we can talk more about this after, because I think I know what you're talking about, but I think the settings are a bit different.
Just to jump in there, the Boltzmann estimator presented as basically like policy gradient from reinforcement learning, just assuming that the state distribution is a Boltzmann. That's basically what you get.
Yeah, so there's been
Related to like techniques from RL and replay buffers and stuff.
Oh yeah, and I was not thinking about. It's more like in like classic Boltzmann learning, you estimate the statistic of the ensemble, and then you update the energy based on the deviation from the target.
Oh,
Just this-
yeah. Yeah, there's definitely related aspects of this with both RL and with what people do in StatMech with reweighting. I think, but there are some differences in especially the types of failure modes you might encounter and how to generalize this to multiple different failure modes. Yeah, so many paths to some of these styles of thinking. Just one more example here is just showing that there are certain observables you can compute better if you use this training procedure. So on the on the top, this is if you're just doing QM training and you're trying to compute some type of diffusivity coefficient, this can end up deviating from what your actual prediction should be, sometimes because the simulation is not stable enough. And if you add this training, you tend to get values that are a little bit closer to the observable that you want to compute. And then one thing I also want to point out is that you can train to one or more system observables, but you can then go and test on totally different system observables to see how well did you capture more behavior than just what you trained on. And so something that was, and I think that there's definitely going to be some correlations here, but something that is interesting is that in this case, this is a radial distribution function. This is not something that we trained on. But by doing this training, we can actually reproduce it better than if we didn't do this training, even though we didn't, it never saw this radial distribution function.
So what was the observable you supervised with?
For this one, it was the intermolecular distance. So totally different.
But we chose the mean as the observable.
So yeah, so this is a case where those heuristics are different. Yeah.
Can you say, if you were to just, I mean, maybe this is a baseline that you've done, but if you were to just take the regular trainings and not use any of the stability aware stuff, but additionally use the objective that you have at the beginning, train on this observable,
Yeah.
is the performance better by doing the stability aware thing, or is it the same?
I think in general, the purpose of rolling out simulations until they become unstable is that generally, like, this procedure works much better if this distribution that you're optimizing over is itself diverse. Like, if all the states are stable already, then like training to observables is not going to help because all your loss is going to be really low. So going and finding unstable regions and then doing the observable loss, we find to be much more effective because there's some diversity in the states you're encountering. You're encountering some stable states, some uncertain states. If you don't do this, then you just have like a lot of useless data, like a lot of stable data that training to the observable doesn't really help.
Yeah, so we're basically seeking out the bad regions and using that to try to correct. And
I think we have done the baseline where we just do it on like the
yeah,
that are already stable and it doesn't really help as much.
And actually, one thing that some other people have been trying to do now with this method is they want to try to use it for things like enhanced sampling. So this might be a way that you can find all of those unstable states in a much more principled manner, much more quickly versus potentially other methods people use like active learning. Great. So so that high-level idea of ML training procedures using simulations, I'll talk about a couple other areas where that actually comes in handy in a few different ways. And I'm putting this all together as the very high-level idea of how this works. So you have any neural network architecture. You have you can project those outputs onto any type of numerical solver. So in the case of molecular simulation, we had some type of symplectic integrator, and that was what you were doing to do the unrolling steps. But there's lots of other things you could do. So when we solve constrained optimization problems, you could use some type of iterative solver. And the key point here is training everything end-to-end with implicit differentiation is the magic to making this work, because now it doesn't matter how we got to the end. It just matters that we got to some point and we can then implicitly differentiate that so that we don't have to actually backpropagate through all of the unrolling steps that we did to get there. And so I think this potentially has opportunities for much more reliable simulations because you're putting certain slightly better guarantees that we get automatically from numerical solvers. And you could also train with different types of information than purely some of the supervised objectives. So here's another example of how that can work. So if you're solving PDEs that are representing complex systems, so the physical world, the whole world can be represented using partial differential equations. And so suppose you have some initial condition here, and the goal here would be that given that initial condition, predict the spatiotemporal behavior over time of the system. And often is the case, some of this spatial behavior is governed by, say, certain types of conservation laws, like conservation of momentum or conservation of mass or other information that we might implicitly know about the system. So if we have this example common scenario where we have limited data, so let's say the training data is all of the green points, And our goal is to predict dynamics much later on in this situation. So in this case, we want to predict much further out than the green points. And let's say this is a super toy example. So let's say that we know that there is some governing ODE that represents the underlying physics, in this case, some type of harmonic oscillator behavior. So if we train the neural network just to those green points, this is a case where it'll fit those green points really well, but it won't do very well at all of the later points because it has no idea what it should be seeing at those later points. But there's this line of work that I think many people here might be familiar with, where you could add that underlying differential equation as a soft constraint to the neural network loss function, and you could optimize over this. This is very colloquially known as physics-informed neural networks, where in this case, you only have the green points of data, and the pink points here represent your spatial discretization. So this could be your spatial discretization where you know some physical laws are going to hold true, and so you know that you can enforce those physical laws on those later points. And so when you combine these two procedures together and you add this soft constraint penalty term, that ends up sometimes helping with the optimization and helping you get to those later dynamics, because you don't have data there, but you know that this type of physics must hold at those later steps. So even it sounds a bit too good to be true sometimes, and in this case, it can be that way, in that there are a lot of failure modes that can potentially come with this type of optimization. This is a very simple transport phenomena problem, and when we actually increase the wave speeds to be really large, this type of approach just does not capture later dynamics for a lot of different reasons. I think this is now something that's been well studied for a number of years, why these failure modes occur. I think it's a mix of difficulties with optimization, difficulties with how you do the discretization, or maybe the inherent error that's coming from the discretization. And coming on this last point here, so at training time constraints, there's possible that it makes optimization harder, but at test time, this might actually be a useful thing to have, because that's going to actually give us some level of trying to enforce some physical reliability. And in this framework, these physical laws are not going to be enforced at inference or at test time on new problems. And so this is where this idea of neural networks and numerical methods can actually come together very nicely. So you can actually take PDE constrained optimization, so the conservation laws that we know and are very interested in. And this is essentially a constrained optimization problem that you can regress on using your favorite iterative method to actually try to solve that PDE, or that set of PDEs, much more exactly. And then by using implicit differentiation, you don't want to backpropagate through all of those steps of the iterative solver. So you can do this instead and train the neural network directly from that type of feedback. And then you can go ahead and test this on a bunch of different PDEs. So the way this works is, so this is an example here, just a 2D problem. So you have a numerical solver up there, and that's the solution that we would like to get the closest to. So if you use this, adding this physical law to the loss function during training, this for many problems, this is pretty hard to converge. It doesn't do so well. But if you use this type of differentiable optimization with your neural network, you can get a bit closer to the right solution. One thing that maybe when you've seen this, it's the case that maybe this is really slow to run an iterative solver on top of your neural network and run that for a bunch of steps. If you have to go through that pass each time at inference, doesn't that become really slow? But you can actually scale that up with something, we do a very mixture of experts like setup. So the same things that have done really well at scaling some of our models in other areas of machine learning, you can apply that same type of setup in this setting. And if you actually do that, you do get a lot of efficiency that comes from that. So this is the much more practical implementation of enforcing physical laws at test time, where initially the blue is how the scaling looks if you're not doing this MOE setup. And if you add the MOE setup after that, that does help get this to a place of more practicality and competitive with numerical solvers. Yeah.
So at training time, you have to solve the key once, right?
Yeah, yeah.
What does, so
So I know what this looks like if you're solving like a quadratic program because you're differentiating through conditions. What
Yeah.
does it look like to solve? I don't know, like the solution of a PDE. What is that mathematical? What is the mathematical object of that?
Yeah. Yes.
Solution operator or?
Yeah, exactly. So you can look for the solution operator. So the first time that we did this, which is represented by the blue curve here, we were strict about, let's make this a QP, let's make sure it satisfies the KKT conditions, let's make sure everything is done really correctly to make sure that we actually do enforce what we think we're enforcing. Later on, we realized that we could just use a nonlinear least squares solver, just like your favorite one for a lot of these problems, and that works just fine to getting you in the right ballpark, and you don't have to do anything super fancy beyond that with your solver. What that means is also that you can do nonlinear problems much more easily, but even linear problems are actually easier to optimize on compared to setting this up as a QP.
So does it mean like it doesn't really depend on how the numerical simulation was generated, like what type of solver it was used, like spectral solver, CFD, DNS?
Yeah, I think this general framework here, you could in theory do this with any type of solver, whether it's a spectral solver, whether it's finite elements. In this case, we use an iterative solver because that works out pretty well with the setup that we have here. But the general framework of this idea of coupling these two things, it doesn't matter that much what the solver is.
Okay, but it means like you need to have a lot of information of how the data was generated.
So actually in this case, we decided to test the extreme where we don't actually use any data on the interior of the domain. So we assume that all we have access to are the conservation laws that the system is going to satisfy, and we just have the initial condition, and we predict whatever that whole solution space is.
I think I can kind of see how picture experts can help with inference speed, because it also lead to like larger training times.
No, it actually is much faster in training time as well. So on the left-hand side, we have the training speed as well. So it's also, so the whole thing is faster. Basically, because you can parallelize across all of the different domains that you care about to solve your problem. So you can do everything in parallel, do that on multiple GPUs.
I think I misunderstood. So you're using the solution of a PDE as a constraint. You're not actually differentiating through the PDE solution.
Yeah, so in this setup, you don't have to differentiate through the PDE solution. The nuances of this are that you actually project onto your solver, you learn a set of basis functions that's going to satisfy the PDE, and then that's the output of that is what you're officially differentiating. So it's a nice way to give you a little more stability, especially when you're actually going and using this downstream for inference. Very last thing I'll talk about is one more flavor of neural networks and numerical methods. I think some of that was touched upon in the questions. Oh, sounds good. Yeah. So spectral methods, I think also something that's come up here where you can actually do some type of basis set expansion on your problem. And that's going to give you some type of spectral space solution, or it's going to give you information about this system purely in a lifted spectral domain. And in this setting, actually, so in the top part, we realized that we can actually train this whole system of learning some solution operator purely in spectral space. And some of that comes from the fact that this grid-based loss that we use with a physics-informed loss can be lifted and done all in spectral space through Parseval's identity. And what that means is that this does end up being a lot faster. It doesn't scale in the same ways with system size, and you do get some better convergence guarantees. So this is another way you can integrate some of the classical ideas that we've had with numerical methods into the neural network setting. Just to show what that looks like, so I wanted to include this because I think sometimes when we use neural network solvers, we say it's much faster than numerical methods, but we're talking about different levels of accuracy, so that numerical method may have been way more accurate. And so I think we should be thinking about doing one-to-one comparisons between these two things. So this is a numerical solver. As your discretization gets finer and finer, your error gets lower and lower. So exactly like how we would want this to behave. And this is a reaction diffusion system, so a chemical system that's maybe diffusing over time. So we have this standard numerical solver in the black line here. And if you do this type of physical space training, so this does mean that you get slower with finer discretizations. It also sometimes means that you're overfitting to the discretization. So when you train on one discretization and test on another, you might be seeing some mismatches between that because of things like aliasing error. And if you use spectral methods instead, that's the blue dot down there, you can get this very nice fast inference for any type of discretization. And the reason I wanted to put this up there is because we really wanted to be careful about doing a one-to-one, same level of accuracy, what is the speed of these two methods. And we also tried this for harder problems as well. So on the top is a numerical solver for Navier-Stokes equations. On the bottom is if you train only in physical space. So you can see that it's not reproducing a lot of the sharp features that we would see in the numerical solution. And in the middle is when you do this training fully in spectral space. Yeah. Yeah, so it depends. So that is true that it depends how large your basis function expansion is. In this case, we were able to find a pretty reasonable value that got close enough to what we would expect towards convergence, but we're not going to like infinite basis sets or anything.
Can you just comment on, is this different from neural Galerkin truncations? Like,
yeah, there's some overlap, I think, with some of the Galerkin methods. I think the key point here was that we do this transition where we can train fully in spectral space through this connection with the sum of the, like, for example, the Fourier coefficients with respect to what the PDE constraint should be. I think the settings are a bit different in that some of the work I've seen there, I think also is a little bit more on the architecture side too. So, okay, I'll go ahead and stop here. So, in summary, a lot of this was actually about general training strategies, thinking a bit about the intersections of numerical methods and simulations with neural networks and machine learning. One of the keys that came up a few times is this idea of implicit function theorem that you can potentially use to train everything end to end. And I'll just pose some questions here. I know this has come up at this whole workshop. Maybe it'll come up more in the discussion today about thinking about ways to bridge modalities of information, whether it's simulation and experimental gaps, whether it's what we train on versus what we're actually going to evaluate on. How do we bridge some of the potential gaps that could arise between those? As well as, can we do things during inference or simulation that are going to correct some of the classic distribution shift problems that we might see in scientific domains when we are very commonly training on one thing, but we expect something that is going to come up when we actually go and run the simulation. And on that note, also just thinking more about evals that we can use to train and correct some of these failure modes that we see. Great. So finally, I get to work with a lot of really great students. So I just want to highlight some of the key people on the parts that I talked about, as well as many excellent funding sources, especially NERSC was actually very useful in training many of these models and keeping us competitive on an academic budget. I'll come back to this summary slide and happy to take any more questions.
When you were comparing with the conventional, so you had the curve of the pin against the what I assume is like a finite element method, and then the spectral method. Mm-hmm. If you used a conventional spectral method, mm-hmm. does that also outperform the finite element method in that case? Yeah, actually, it's a good question. So we tried a few different spectral methods here. Actually, this one that you see here is it's an operator splitting method, and that seems like it's pretty much whatever is the most standard approach for solving like a reaction diffusion system. Got it. Thanks. Yeah.
Thank you. Going back to the molecular dynamics force field training, it seems like right now there's a set of force fields that optimizes for different things, you know, speed of execution for classical force fields versus maybe accuracy for some more quantum mechanically informed ones. And if you had to prioritize what you think the neural network approach can what niche you want it to fill. Is it matching DFT but faster, or is it reproducing certain condensed phase observables better, or like how do you think about what its niche is?
Yeah, I think the ultimate goal of doing these simulations is to reproduce observables of the systems that we care about. So it's good to get low energy and forces error, but at the end of the day, we want to be able to actually learn something new from these simulations. And that often is what we're going to get when we actually run this out for some level of time steps. What's the behavior that we observe from that?
And do you think about evaluating that by still running MD simulations using this force field to observe the variables directly, or do you think about sampling in the sort of way that you described in your step 2 to estimate them?
I think ultimately to do full evaluation as a case study, you would want to run these out over time and just see how things behave, because that's also going to be a critical part of, can we actually trust these simulations and do reliable simulations?
Thank you.
Thanks for the talk. I have a question about instability for simulation. So if, for example, if your simulation crashes at some point, that means the potential is not perfect. But that doesn't mean that other part is just bad. Is there a way, but also if you have run a long time, you don't really want to get rid of the data that you have run. I'm just wondering if there's a way to decide if the simulation that you have run is actually usable.
So you mean you run it for long time scales, it did okay in the beginning, but then it didn't do so well after that?
Yeah, so if you run for a long time and then crashes and the simulation is not perfect, but do you think there's a way to decide if the part prior to the failure is still usable?
Yeah, actually that's an interesting point, and it actually comes back to this point that there are some people now actually using this method to do some type of enhanced sampling. So they're exactly trying to run the simulation, keep the parts and be aware of the parts that work, and then take the parts that don't work, and actually that's what they're putting back into their training cycle to retrain on.
Thank you.
Yeah, thank you. So also on instabilities, you mentioned this perspective that you could be in some weird part of your potential landscape and you haven't actually converged to the underlying thing. But there was also like, I don't know if they were cartoons or not, but like the fraction of unstable simulations kind of just goes up. And so there's this other idea that maybe you just accumulate errors over time and like your actual network doesn't actually cover the function you want to approximate. How do you think about those two regimes?
Yeah, so that's definitely something that's possible to happen, that as you simulate over time, your unstable trajectories are going to keep going up. The goal is that there are fewer and fewer unstable trajectories that are going to come up. And I think by the time you finish doing this cycle of fine-tuning, you hope that all of the trajectories that are left are like the really, really hard ones, that it's hard to get full coverage and correct every single one, especially because of these competing objectives. But you hope that by the end of that, the reason you're able to simulate more stably is because you've corrected everything but the hardest ones.
Okay. And the thought is that the underlying like model architecture has the capacity to learn the actual like potential landscape. And I guess to that, if that's the assumption, then like, do you guys also do scaling with like different size pre-trained models, for instance, and seeing how errors propagate?
Yeah, that's definitely something that we are looking at more generally. This is the point of a lot of the training strategies that I presented here, is that it is architecture agnostic. So maybe in 3 years, we'll have a really good architecture that scales really well. You could still add this training strategy on top of that.
Thanks.
In the interest of time, we should close up now, and we will reconvene at 1:30 for the next talk.